السلام عليكم ورحمة الله وبركاته. Okay, all right. Yeah, we finished chapter 7, and now we move to chapter 10, okay, which is flow in conduits, or basically pipe flow. So we will take this chapter, and these are the conceptual knowledge to be derived from the chapter, the procedural knowledge, and typical applications for flow in pipe, pressure drop, and head loss. Okay. So here, most of this, some of these things we have already looked at them previously, most especially under viscosity, where we looked at how viscosity varies in a pipe and the velocity profile, and developing and fully developed flow, and also some of them under flow types like steady flow, uniform flow, and all that. So we discussed some of the components of this chapter sparsely, or this in some of the previous sections that we discussed, but here we'll present a more systematic approach to all that has to do with pipe flow. Okay. So flow in conduit, and what is a conduit? Conduit is any pipe, tube, or duct that is completely filled with a flowing fluid. Notice this: completely filled. You can have a conduit that is not completely filled, and that is classified under open channel flow, not pipe flow, if it's not completely filled with the flowing fluid. And examples include a pipeline transporting liquefied natural gas or water, a micro channel, that's a very small channel transporting hydrogen in a fuel cell, and a duct transporting air for heating a building. Okay, so a duct, which is also like a pipe, a passage in general. Okay. A pipe that is partially filled with a flowing fluid, e.g. drainage pipe, is classified as open channel flow. So partially filled, it means it is not completely filled. Okay, if it is not completely filled, it is classified as an open channel flow, not pipe flow. Okay, and open channel flow, we are going to look at open channel flow in chapter 15. That will be next week. Okay, because after the pipe flow, we'll look at open channel flow in chapter 15. Okay, that will be next week. And the terms pipe usually is applicable to circular. When the cross section is circular, we call it pipe. And if it is another cross section that is non-circular, you can have rectangular, square, and any other shape, any other cross-sectional shape apart from circular, we call it duct. Okay, duct. And conduit are usually used interchangeably for flow sections. Okay, conduit, you can refer to pipe, you can refer to duct. Okay, and the circular pipes can withstand large pressure differences between the inside and the outside without undergoing any significant distortion, but non-circular pipes do not. Okay, when you have a pipe with water flowing, okay, there is pressure inside, and then there is pressure due to overburden. Maybe you have soil, because usually pipes is buried under the soil. Okay, so pressure is being exerted by the weight of the soil. Okay, and there's pressure inside, so you have pressure difference. Okay, from due to the flowing fluid inside the pipe and due to the weight of the overburdened soil above the pipe. Okay, so circular pipes have the capacity to withstand large pressure differences. Okay, meaning they can carry huge pressure inside while the outside pressure is low. Okay, so that's the pressure difference. Okay, so without undergoing any significant distortion. But non-circular pipes may not be able to withstand such large pressure differences. Okay, that is why more often than not, whenever we are referring to conduits, most of the conduits used, the cross-sectional section is usually circular because of the large pressure differences that pipes can withstand. And basically, the types of flow inside pipes are classified into two, laminar and turbulent. If you remember, under the classification of flows, we briefly discussed about laminar flow and turbulent flow. Okay, so now again, we will look at laminar flow, analyze the flow, make some derivations with respect to the parameters, affecting laminar flow, and then we will look at turbulent flow as well, all as they relate to pipe. Okay. So, like I mentioned earlier, some of the concepts we are going to discuss here will not be entirely new to you. Some of the concepts we have already discussed, and some are not were not discussed previously. Now, classification of flow using motion. Okay, laminar flow, which is simply the flow in the laminar flow, we know that the flow particles move in layers or streamlines, or what we call laminae. That is the laminae, the Greek word for layers. They move in layers, okay, in layers, and the effect of viscosity in this case is so large that fluid particles move in parallel layers, okay, due to viscosity. So each layer is having a different forward velocity, and mixing here is very small. Okay, it's only due to molecular diffusion, okay, that you have mixing in laminar flow. So laminar flow, usually it has low velocity. That is why the fluid particles can move in layers without mixing, and it is encountered when highly viscous fluids such as oils flow in small pipes or narrow passages. Okay, normally it's applicable when you have high viscous fluid like honey, like milk, which is thick. Okay, when the viscosity is high, so it moves slowly and in clearly defined layers or streamlines, okay, without mixing. So here, as we mentioned, the effect of viscosity is very high. What about turbulent flow? Is the opposite of laminar flow. Here, in this case, the fluid particles, they move at high velocity and at a random motion in all directions. And viscosity effect here is very small, okay? And the friction factor reaches a maximum when the flow becomes turbulent, okay? The friction factor, we will discuss about friction factor, okay? F, we call it F, friction factor. We'll discuss about friction factor in the few slides to come. It reaches a maximum when the flow becomes turbulent. It reaches maximum because it is a function of the shear stress, okay? It is as well as the velocity, as we are going to see the exact definition, the mathematical definition of the friction factor. And if it becomes maximum, it means you have the head loss is higher. Okay, the head loss is higher in turbulent flow. Of course, another issue because of the velocity. Now, laminar versus turbulent flow. In laminar flow, we say the fluid particles move in clearly defined layers. In layers, you can see in layers without mixing. Okay, so they move in clearly defined streamlines. You can see, the streamlines here are parallel and collinear. Okay, they are parallel and collinear in which flow? Who can tell me? They're parallel and collinear in uniform flow. Because in this case, because they are parallel and collinear, it means the velocity gradient, the tangent to the streamline, which gives the direction of velocity, is the same throughout. So here velocity is constant throughout. Okay, they are parallel and collinear. Okay, for steady flow, like I mentioned before, they can be parallel, but they can be collinear or straight, but not all parallel. Okay, because when you have a duct that is closing, oh, uh, when you have a converging duct, you see here the streamline can be straight, but they are not. They can be straight, but not parallel. Okay, not parallel. But this is for the case of uniform flow, in which they are straight and parallel. Okay, and here you can observe, when you in laminar flow, here you have a tube where you inject a dye. A dye is a colored substance whose movement can be noticed. If this pipe were to be, let's say, transparent, when you inject a dye here, you will see how it is moving. Okay, it will move straight, okay, without any distortion, without any mixing. If the flow is laminar, that is depending on the average velocity v. Okay, now when you inject it, if the flow is turbulent, you will see the dye mixing up. You can see that it is mixing up. It is moving in random motion, and that is because of the high velocity of flow. Okay, that is indicative of that is prevalent in turbulent flow. Okay, so in turbulent flow, you have mixing, ading. The fluid particles are mixing in all directions, and the streamlines are not linear. Okay, the streamlines are not clearly defined as in laminar flow. Yeah, this is another experiment that's conducted, by Reynolds, who's an English scientist that, studied laminar and turbulent flow. The same thing when you inject a dye here at low velocity, the dye moves clearly defined layer. Okay, when you now increase the velocity of flow, there is mixing. Okay, it begins to mix, and there is clearly ading, that is rotational motion. As you can see, it is mixing. Okay, that is in turbulent flow, and this is in laminar flow. And Reynolds discovered that there is a relation between the state of flow, that is laminar or turbulent, and density, velocity, diameter, and dynamic viscosity of the fluid. Okay, at the end, the formula for the Reynolds number, defined as Re, given as R small letter e. Okay, sometimes we use rho Vd over mu. Okay, Vd is the pipe, d is the pipe diameter. Okay, of course, you know that more, which is kinematic viscosity, is more over the density. So if you can replace more mu over rho, you put more. Okay, so either this or this one. Okay, and from here, if you replace v with q over a, as v is q over a. Okay, and for pipe, area is pi d squared over 4. So this is 4q over pi d squared. So, and then when you substitute v as 4q over pi d squared, you will end up with 4q over pi d more. Okay, and then again, this is in terms of the mass flow rate. Okay, you know the mass flow rate, which we did before, is rho q. Okay, so here, if we substitute q, if we want to substitute q as the mass flow rate divided by density, okay, if we replace q with this mass flow rate over density, we will end up with 4 m dot divided by pi d more. Okay, so this is the general formula for the Reynolds number. Okay, the different formulations, but how was it derived? Okay, the Reynolds number is simply defined as the ratio of inertial forces to the viscous forces. Okay, inertial forces to the viscous forces. What are inertial forces? Inertial forces are the forces acting on a body according to Newton's second law of motion, that the vector sum of all forces acting on a body is equal to the mass times the acceleration, and acceleration is simply dv dt. Okay, simply dv dt. Okay, so, and inertia is mass times velocity. Okay, so this is simply rate of change. The sum of all forces acting on the fluid element is equal to the rate of change of momentum. Okay, inertia is due to the mass of the body, the tendency of body to remain at rest if it is at rest, or to keep on moving if it is in motion. Okay, so this is the inertial force. Okay, ma is the inertial force. Okay, ma is the inertial force. Now, how do we get this rho v squared over L squared? Okay, here we use a representative length. Okay, mass, as we know, mass is what? Density times volume. So volume will represent as L cube, where L is representative length or characteristic length. For cube, it will be L cube, isn't it? And then for the acceleration, we have the velocity over time. Okay, but don't forget, we can divide this into L squared v times L over t. And L over t, that is distance over time, is also velocity. Okay, so we can have it L squared v times v, so which is rho L squared v squared. Okay, so this is the inertial force from the Newton's second law of motion, ma. Okay, then what about the viscous force? The viscous force is from the same Newton's law of viscosity. Okay, from Newton's law of viscosity, that the shear stress is proportional to the velocity gradient v over L. Okay, and then the viscous force now F is shear stress times area. Okay, and shear stress is mu v over L, characteristic length, and area we just use L squared as the characteristic length. So L cancel L, so we have mu VL. Okay, so that is how we obtain mu VL as the shear viscous force. Okay, so and then when you divide, you can see L will cancel L, V will cancel the square, and then you will be left with rho VL over more. Like I said, and mu over rho is more. Okay, L is the characteristic length, which is equal to diameter for pipe flow. Okay, for open channel flow, we call it hydraulic radius, which is area over weighted perimeter. Okay, for open channel flow, instead of diameter, we use R, which is hydraulic radius. This we will explain in chapter 15 as well. But for chapter 10, where we are dealing with pipe flow, our characteristic length L is the pipe diameter. Okay, so this is a simple derivation of the Reynolds number. So by and large, Reynolds number is one of what we call pi groups or non-dimensionless numbers. Okay, we call them dimensionless numbers. Okay, because you can see its ratio of forces. So it has no unit, so it is dimensionless. Okay, we call them dimensionless numbers or pi group. Okay, and by definition, it is simply the inertial forces to the viscous forces. Okay, so of course, we will see that for laminar flow, where the viscous force dominate, we will have low Reynolds number because the velocity is low. Okay, and the viscous force, the denominator is higher. Viscous force dominate, so the Reynolds number will be lower in laminar flow than in turbulent flow. In turbulent flow, we have the inertial forces dominating. Okay, we have the inertial forces dominating. Okay, and the inertial force is simply the sum of all the forces acting on the fluid element. This include, the pressure force, the gravitational force, as well as the shear force. Okay, and any other force that may be acting on the fluid element as it is moving. Okay, so for turbulent flow, we have the viscous force is not dominated by the inertial force. So we have the Reynolds number to be greater, and that is because the velocity is higher in turbulent flow. So we will see the ranges for the Reynolds number for both laminar and turbulent flow. Usually, different texts use different values sometimes, okay? But for laminar flow, Reynolds number is up to a value of 2,000. Okay, some text like the other reference I am using, which is by Yunus Chengel, is they are using 2,300. Okay, as the upper limit of Reynolds number for laminar flow. Okay, and then you have what is called transition zone. That is when the flow is changing from laminar to turbulent. Okay, so here they call it unpredictable, or we can call it transition. Okay, transition zone. Okay, which is when Reynolds number lies between what 2,000 to 3,000. Some texts are using 2,000 to 4,000. Okay, as the transition zone. And turbulent flow in this text is anything greater than 3,000, while some texts are using anything greater than 4,000, okay, to be the turbulent flow. Okay, so like I said, some texts use different numbers, okay, because of the results which they observed in the lab. Okay, but in this text, 2,000 to 30,000 is transition, and anything after 3,000 is turbulent flow. But don't be surprised if you check other texts to realize that turbulent flow starts from 4,000 and laminar up to 2,300 instead of 2,000. Okay, and all this is tied to the velocity, Vd over mole. Okay, you can see at lower, when the velocity is low, Reynolds number is low. When the velocity is high, Reynolds number is high, as in the case of turbulent flow, where the velocity is definitely higher than the velocity in laminar flow. Now, if you remember, we also discussed, under the different types of flows, developing flow and fully developed flow. We even use something like this figure where you have water entering into a pipe and the flow is developing. Okay, at the entrance, you have like a uniform flow, okay, where it is uniform, okay, and then the velocity profile keeps on changing as the flow is progressing streamwise, in the streamwise direction. Okay, as the flow is developing, the velocity profile is becoming flattened, it's becoming more parabolic. And what happens here is simply because of the boundary layer. At the entrance, the shear stress is highest at the entrance. The shear stress is highest at the entrance, but the shear stress keeps on reducing in the direction of flow, that is in the streamwise direction. As you can see, it is highest here at the entrance. Okay, this is the wall shear stress, which is reducing. The wall shear stress is changing due to the change in velocity profile as boundary layer grows. The shear stress is times the velocity profile, dv dy. Okay, so the velocity profile is highest at the entrance, and that is why the shear stress is highest. As it is moving, the velocity profile is becoming flattened. Okay, it's becoming flattened, so dv dy is decreasing, and that is why the shear stress is also decreasing in the streamwise direction. Okay, but it becomes constant when you have when the flow is fully developed. That's when the velocity profile is not changing with time and distance. Okay, if the velocity profile, like in this case, when it is fully developed, okay, so you have the same velocity profile at subsequent sections. So the velocity profile remains constant. This is constant, the viscosity of the fluid, hence the shear stress will also remain constant, in the direction of flow. Okay, and that is when the flow is fully developed. And in this case, the velocity, as we are going to see, initially is a function of r and x, but that's in this case. But in this case, when it is fully developed, it is no longer a function of x. It becomes constant with, let me say, s in the direction of flow. So it becomes only a function of r, meaning it varies along the radius, okay, not along the direction of flow. Okay, and that is why we say it is one-dimensional. Okay, it is one-dimensional. When it is fully developed, the flow becomes one-dimensional. Okay, but before it becomes fully developed, the fluid particles are accelerating up to when it becomes fully developed, because the velocities of the fluid particles are changing. If you look at the center line, okay, you can see this is shorter, this is bigger, so it's increasing, that is accelerating. When the velocity is increasing with time, we say that the fluid particles are accelerating. So that is the region within which the fluid particles are accelerating. Okay, and the length within which the flow becomes fully developed. Okay, by fully developed, it means the velocity profile stops changing with distance, is called the LE, okay, which is the entrance length. Okay, we call it entrance length or entry length, L subscript E. Okay, so it's the length within which the velocity profile becomes constant. And here you have the boundary layer increasing with distance. Okay, it is smallest at the entrance and the boundary layer keeps on increasing. Why is the boundary layer increasing? In order to ensure that the mass flow rate is maintained. Because at the entrance, once the flow entered into the pipe, it experiences drag, the shear stress. So those that are touching the walls of the pipe, they assume zero velocity. And when they assume zero velocity, they stop moving. And the flow rate, for the flow rate to be maintained, for the mass flow rate to be maintained, the particles in the middle have to move faster so that the mass flow rate at any given point in time is constant because there is no accumulation, there is continuity. Okay, the continuity equation plays a role. There is no accumulation. Okay, so that is why the particles in the middle now move faster at faster rate than those close to the walls to maintain the same flow rate. And then the boundary layer now is increasing. That is the region within which the viscous forces are having significant impact. Okay, that is the edge of the boundary layer. You can see it represented with a dashed line. So this is the boundary layer which is increasing. You can see it here. It's increasing up till when it becomes parallel to the center line streamline. And this is the potential curve for inviscid flow, where the flow is not affected by viscous forces. Okay, or we can call it also irrotational flow area. Okay, we'll explain more with the subsequent figure as well. And we will formulate how do we find the entry length, okay, the entrance length for laminar flow and for turbulent flow. For laminar flow, it is LE over D equals 0.05 RE, okay? And for turbulent flow, LE over D equals 50, okay, for turbulent flow. Okay, so this is the formula for finding the entrance length for laminar and turbulent flow. Okay, so this is another figure again, which is buttressing, bringing some of the salient points as it affects the developing flow and fully developed flow. Okay, so here, like I mentioned, if you consider it, the fluid particles in the layer contact with the wall are come to a complete stop. Okay, and this layer causes the fluid particles in the adjacent layers to slow down gradually as a result of friction. Okay, this is moving at so value, and this one stopped. It's like you are moving with someone, you are holding someone's hands and you are moving together, and then suddenly that person stops. So definitely, as soon as he stops, you either stop with him or you will have to release his hand and then keep on moving. But no matter what, he's going to slow you down. And that is why the adjacent layers are gradually slowing down as a result of friction. Okay, and to make up for the velocity reduction, the velocity of the flow in the midsection of the pipe has to increase to keep the mass flow rate throughout the pipe as constant. Okay, the mass flow, because there is no accumulation, so the mass flow rate is constant. Inflow is equal to outflow. Okay, and that is why the velocity gradient develops along the pipe. Okay, when it enters here, it enters as uniform flow. Each particle at a given section, the particles are having the same velocity. The same average velocity is attributed to each of the particle across R. Okay, but due to the shear stress affecting, as it moves a distance x, you can see the velocity profile is changing. Okay, because of the no slip condition, those in contact with the wall will assume zero velocity and will slow down the adjacent particles, thereby creating the velocity boundary layer, or simply the boundary layer, okay, which is indicated here with the red color. Okay, and then the velocity profile keeps on changing, okay, elongating, becoming parabolic. This is the average velocity, and this is the actual velocity distribution. okay, and then until it becomes fully developed, okay, until this is what we call the hydrodynamic entrance region, or simply the entrance length, like in the other one, the entrance length, and here it is fully developed velocity profile. So thereafter, it maintains the same velocity profile in the S direction, okay, or in the streamwise direction. The velocity profile does not change anymore. And this is the boundary layer, and the region here is called the irrotational or inviscid flow region, in which the frictional effects are negligible, okay, and velocity remains essentially constant in the radial direction, okay. We are going to develop some formulation for the velocity profile and see why is it parabolic. Did we just assume parabolic, or this can be supported mathematically? Now, the thickness of this boundary layer increases in the flow direction. This I also explained, and here he called the entrance length as the hydrodynamic entry length, LH. So LH or LE, they are just the same. I mean, they are all referring to the entry to the entry length. And then the flow becomes fully developed when the normalized temperature profile remains unchanged, meaning it remains constant. And fully developed flow is equivalent to fully developed flow when the fluid in the pipe is not heated or cooled, since the fluid temperature in this case is essentially the same, okay? And the fully developed region is parabolic in laminar flow, okay? It is parabolic in laminar flow. In turbulent flow, it may not be parabolic. It will be more or less like a plug. Okay, this we may see later. Okay, so this shape is parabolic. Okay, and this is the average velocity, and we are going to see later for fully developed that the average velocity is simply equal to the maximum velocity divided by 2. Okay, the maximum velocity occurs here, isn't it? Because velocity is maximum in the center line. Okay, this we discussed when explaining the shear stress, okay, under viscosity, that the velocity is maximum at the center. And here we are going to also prove that mathematically. Okay, if you remember, we have explained this figure before. Okay, but here we are again explaining it more and more, and we will support it with the relevant mathematical derivations as well. Okay, so you see here the shear stress is maximum here at the entrance, and then it becomes constant after when the flow is fully developed. Okay, it becomes constant, and the velocity is initially varying with r and x, but when it is fully developed, it becomes a function of r alone. Okay, meaning in the vertical direction, it varies only in the vertical direction, not in the horizontal direction. So it becomes one-dimensional. It is fully developed. Okay. Now, let's take some example here and see here classifying flow in conduits. Consider if fluid flowing in a round tube of length 1 meter and diameter 5 millimeter. Okay, so this is the tube. The length is 1 meter and diameter 5 millimeter. Classify the flow as laminar or turbulent and calculate the entrance length for air at 50 degrees with a speed of 12 meters per second, and B, water at 15 degrees with a mass flow rate of 8 grams per second. So to classify the flow as laminar or turbulent, all we need to do is to find the Reynolds number and look at the value of the Reynolds number. Simple. Okay. For air, the kinematic viscosity, this is the value, and for water, the dynamic viscosity is this, okay, Newton second per meter square. And the assumption says that the pipe is connected to a reservoir. The entrance is smooth and tapered, okay, so that there's minimal head loss. And determine, so the goal is to determine whether each flow is laminar or turbulent and to calculate the entrance length for each case. Okay, so for air, we use the Reynolds number, simple Vd over mole. We have the velocity of flow, which is already provided as 12 meters per second. We have the pipe diameter, and we have the air kinematic viscosity. So this is 3,350. So based on the definition of turbulent flow in this text, which is 3,000, above 3,000, the flow is turbulent, okay? And to find the entrance length, that is the length within which the flow is developing. That's the entrance length, simple. The entrance length is the length within the pipe that the flow is developing, meaning the flow profile, the velocity profile is changing in the direction of flow. Okay, so the formula is LE equal 50D. Okay, so this is the length, 0.25 meters. Now, when we have water in the second case, we use the form because we were given the mass flow rate. So we use the Reynolds number formula, which has the mass flow rate. Okay, and we can derive this from this one, from the basic one. Okay, by substituting changing the velocity to Q and changing Q to mass flow rate. Simple. Okay. So here we substitute the values. Okay. And this is the Reynolds number 1,700, which is less than 2,000. So the flow is laminar in this case. And the entrance length for laminar flow is given by this formula. Okay. So this is now the length within which the flow is developing. Okay. I hope it is clear. Any question? All right. Now we are talking about pipe. Let's briefly talk about the pipe diameter, okay, or something called the nominal pipe size, okay, NPS, nominal pipe size. So the nominal pipe size determines the outside diameter, or OD. OD is outside diameter or outer diameter of the pipe. Okay, so for example, pipes with a nominal size of 2 inches have an outside diameter of 2.375 inches, meaning, you know, the thickness of the pipe is now 2.375 minus 2, which is 0.375 inches, which gives the thickness of the pipe. Okay, once the nominal size reaches 14 inches, the nominal size and the outside diameter are equal, okay, once it reaches 14 inches. So the nominal size and the outside diameter are equal. That is, a pipe with a nominal size of 24 inches will have an outside diameter of 24 inches. And a pipe schedule is related to the thickness of the wall. Okay, this is a pipe. This is the inner diameter or inside diameter, ID, and this is the outside diameter. So this is the pipe thickness. ID, OD minus ID. OD minus ID is equal to the pipe thickness. Okay, and the pipe thickness here, pipe schedule is related to the thickness of the pipe. Okay, what is really schedule? The original meaning of schedule was the ability of a pipe to withstand pressure. Thus, pipe schedule correlates with wall thickness. The bigger, the more the thickness, the more the pipe schedule. Okay, so a larger schedule indicates thicker walls. Okay, a schedule 40 pipe has thicker walls than a schedule 10 pipe. Okay, so each nominal pipe size has many possible schedules that range from schedule 5 to schedule 160, depending on the condition that it is going to be used and depending on the pressure that it is going to work under, depending on the working pressure, because the schedule, as we mentioned earlier, is simply, the ability of a pipe to withstand pressure. Okay, so this is the nominal pipe size. Okay, half inch. You see, half inch, that is 0.5. You can see that it's 40 schedule and 80 schedule, and this is the wall thickness. 80 schedule is greater than 40 schedule. Okay, for pipe inch, for nominal pipe size of 1, you have the internal diameter to be 1.049 or 0.957, and you have 2 schedules, 40 and 80. So when it reaches 14, that is when the nominal pipe size and the outside diameter are equal. Okay, but before that, you can see in most of the cases, in all cases, the outside diameter is greater than the nominal pipe size. Okay, the outside diameter is greater than the nominal pipe size. Okay, except for 14. When it is 14 inches, then the outside diameter and the nominal pipe size are the same. Okay, from 14 upward. Okay, you see 24 also, 24 inches. And then you have different schedules. Okay, depending on the wall thickness. Okay, because as the schedule increases, the wall thickness increases as well. Okay, and if you see here, as the wall thickness increases, the inner diameter or the inside diameter decreases. Oh, let me use this increase. No, as this increases, okay, this increases downward, but this one is decreasing. Okay, the inner diameter of the pipes is diameter is decreasing. Okay, so when we say nominal pipe size, if the nominal pipe size is greater than 14, from 14 upward, then that is equal to the outside diameter. This is very important that we need to understand. Okay, and flow in conduits. What are the components of the energy equation? This we have seen from the energy equation, that these are the components of the energy equation, where HP, is the pump head, HT is the turbine head, and HL is the head loss. Alpha is the kinetic energy correction coefficient, okay? Alpha 1 and alpha 2, which we call Coriolis coefficient, which is equal to 1 for turbulent flow and is equal to 2 for laminar flow, okay? This we explained in chapter 7, okay? So what is head loss? We explained that total head loss, which is HL, is simply the pipe head loss plus the components head loss, okay? Or simply, the pipe head loss is sometimes called major head loss, and the components head loss is sometimes called minor head loss, because this components head loss is due to the losses in valves, fittings, vanes, and all that, and they are very small compared to the pipe head loss or major head loss. And the major head loss is simply the frictional head loss. We call it frictional head loss, or H subscript F, because it's the major head loss occurring in pipes, which is the head loss due to friction or shear stress at the walls. Okay, so the pipe head loss, this section presents the Darcy-Weisbach equation, which is used for calculating head loss in a straight run of pipe. And this equation is one of the most useful equations in fluid mechanics. Okay, the Darcy-Weisbach equation. And the pipe head loss is one type of head loss. Okay, and the other type is called component head loss. Okay, and all head loss is classified using these two categories. Total head loss equal pipe head loss plus component head loss. And the component head loss is associated with flow through devices such as valves, bends, and T's. T's, it means like joint, T joint, okay? When there is flow, when it is separating here and there is head loss due to the bend, okay? And pipe head loss is associated with fully developed flow in conduit and is caused by shear stresses that act on the flowing fluid. And we should know that head loss is sometimes called major head loss. The pipe head loss is sometimes called major head loss, the component one minor head loss. And pipe head loss is predicted by Darcy-Weisbach equation. Okay, so in the next class we will derive the Darcy-Weisbach equation, which is this one, and then move on. Any question before we call it a day? You can see today we are 15. Is it 15? One guy is absent. It's not. All right. In the absence of any question, see you tomorrow, where we hope to conclude this chapter, so that next week we will begin a new chapter. Okay.